Hello students. Over the past two lectures, we were looking at how we go about designing a hardware that would execute instructions one at a time, right? And we slowly started introducing few hardware components that would help us to achieve this, right? And we looked at the arithmetic and logic instructions, and then we extended the same hardware. By adding few additional modules to handle the data transfer instructions, that is the loads and stores, right? So here is the overall uh, hardware that we built. We assume that there will be a register file and which has two output ports and one input port, which would be driven by clock, and then we assume that there would be an ALU that will help us to carry out all the operations as specified by the ISA. And in addition to that, we have introduced some additional muxes, mux B, mux Y, and few additional buffers, right? RZ, RY, and RM that would help us to handle the instructions, the ALU and data transfer instructions, in the five steps that we have initially started with, right? Those are the logical steps, and we try to recreate that in the hardware, right? So in the second step, when we look at the instruction register, or rather when the control circuit would look at the instruction register, it would decide the rs1, rs2, rd and immediate fields, and it would extract that from the ir and keep them ready. And in the same cycle, or in the same step, right? Sorry, that's not the cycle. So in the same step, that is step 2, we would contact the register file, and we would read uh, the values that are present in rs1 and rs2. Here they are labeled as a and b, and keep them ready. In the third step, what happens is, based on the instruction, we would pick the select line for mux b. Basically, the control signal would be generated by the control circuitry, and the both the inputs of ALU are now decided and ready. The ALU would perform the operation that it's supposed to. Again, the operation to perform will be dictated by the control circuitry, and by the end of step 3, the value whatever is there has been whatever is the output of ALU will be returned to a temporary buffer or register, which is RZ. Right, in step 4, based on whether it is a load store instruction or an ALU instruction, we are going to divert RZ either to MAR for load and stores, or we are going to drive it to mux Y. And if it is a load instruction, then the um, memory would respond us with the data in MDR, and that would be the other input to mux Y. And if it is a store instruction, the value in ry would be given to mdr, right? And the interface between the processor and the uh, memory, which is the processor memory interface, let's assume that it is abstracted with the registers MAR and MDR, right? And when these registers have to pick the values and all, again would be determined by the control circuitry. Following that, by the end of step 4, we will also determine whether we have to pick the value from MDR or RZ as a select line to mux Y. And that would be the value that is stored in ry. And in step 5, we would update the register file if it is an ALU instruction or load instruction. For store instruction, we don't do anything. Now, in the at the end of last class, I mentioned that MuxY would also be having one other input, which is the return address, specifically for the control instructions. Now, in this lecture, we are going to concentrate mainly on the control instructions and see how this hardware that we have built so far would handle them. So let's move on. So the control instructions primarily affect the program counter, as you are aware of it, and the value of program counter will be used in the fetch step itself. So we'll start with the instruction fetch deep dive. And also, if you noted, we did not talk about step 1 in the ALU instructions or load store instructions also. Now we would expect that a value is present in the PC. To that we add another value which is equivalent to instruction width, and because we are looking at RV32, each instruction will take 4 bytes, so consecutive instructions would be 4 bytes apart. So these values can be given to an adder, and the output of that adder would be PC plus 4. Typically that would be the memory address of the next instruction, and that's what would be given to the MAR, right? And the same would be the input to will be driven as an input to the PC for the very next instruction, right? So let's say we have started our execution with an address 0. The very first output that would we get from the ADD, the adder, would be 4. Then 4 would be written back to the PC. Then the next output would be 8, 12, 16, so on and so forth, right? This all seems almost perfect for the the sequential instructions, where the very next instruction that we want to execute would be just the immediate instruction. But how do we support the branch and jump instructions, because they are going to affect the PC? Let's see how we go about it. Let's consider two examples, one for branch BEQ x1 x2 label 1, and the other is jump JL x1 label 2. So what we expect the BEQ instruction to do is compare the values in x1 and x2, and if they are equal, then we would expect the control to jump to the location PC plus label 1. The same thing would happen in JL, but unconditional, right? No matter what the value in because there is no condition check, when we execute JL x1 label 2, the next PC would be the current PC plus label 2. Now let's try to understand them step by step. So we introduce a small modification. Instead of having 4 all the time, now we are introducing another mux inc here, and to that one input would be the instruction width and other would be the immediate value that we get from the instruction register, right? Now we need to determine whether we have to pick 4 or the immediate value, right? Accordingly, the next PC would be generated and sent to MAR, and the same PC would be fed back to the PC register, so that in the very next step we can get the next PC or next to next PC in that sense, right? And I'm also introducing a temporary register PC temp, which would take a copy of PC. Now when it takes a copy of it and how do we use this, we are going to look at it as we go, and this would be the input to muxy that I mentioned earlier, the written address. So let's try to take it step by step. In the step 2, the branch offset will be set or calculated, and at that time we'll also know that the instruction we are trying to execute is BEQ and the values in x1 x2 are ready with us. In step 3, the values in x1, x2 are compared within the ALU, and ALU would tell us what is the output, whether they are equal or not equal. And that would be the select line to the mux INC, right? And if you look at the JL instruction, in step 2, we'll identify that it is JL, and we'll also keep ready the branch offset. In step 3, there is nothing to check the condition or anything like that. So in step 4, we are going to select the mux INC as up, so that it would pick the immediate value and not 4. And at the same time, we'll also take a copy of PC in PC temp and send it to muxy. So if you remember, by the end of step 4, muxy would pick one of the inputs and write it into register ry. And in step 5, for branch, we don't do anything in particular, but for JL, the return address, now if you look at what's the value in PC temp, it would be PC plus 4 before the jump has happened. So that value will be returned to the register, which has been given as RD here. Now, in order to achieve this small operation, in the very first step, when we take the PC and send it to instruction fetch, we also calculate PC plus 4 and take a copy of that in PC temp. Okay, so that PC temp would be used in step 4 for JL. Moving on, let's see how we can support JLR. Yes, we have introduced some additional mux in calculation of PC, but let's take an example, JLR X30X1. Right now, this is the circuit that we have so far in the instruction fetch step. Right now, we have introduced one other mux, which is mux PC here. Right, earlier the input, there was only one input to the PC, which was kind of feedback, you can say, which would be the output of the adder given to the PC. But now here we are going to make a selection whether it should be the return address or the output of the adder. Right, how do we go about it again? Let's look at it step by step in 5 steps of a JLR instruction execution. In the very first step, like I mentioned, the PC will be incremented and the value is kept in the PC temp. And in the second step, we are going to identify that the instruction which we are trying to execute is JLR, and we'll also identify that X1 is the source registers, there is an offset 0, and X3 is the destination register. Right, and in step 3, earlier for JL there was nothing to happen, but for JLR in step 3 we are going to calculate the next PC with the value of RA as the value in X1, and 0 is the immediate value. It means that the select lines for mux PC and mux INC will be selected appropriately, and that would be added and kept ready. And step 4, the value in PC temp would be given to mux Y, and that will be picked and written into register RY, which will eventually update the value in the register file, specifically the value of X3. Now, by the end of step 5, if you look at it, the next PC would be the value of RA plus the immediate value. Right, that's how we are going to achieve supposedly the jump effect. Right, the very next instruction we are going to fetch would be the location which is given by the value in X1 added to an offset 0 in this example. So the control signal will appropriately drive the select signals here. Sorry, the control circuitry will appropriately drive the control signals here. Now moving on, all the logic that we have seen can be abstracted as if they are present in a block which is called instruction address generator, IAG to be short, and at the end of it we get the value of PC, which would be given now to a mux, which is mux MA. The other input to mux MA is RZ. If you remember, that would be the uh, output of step 3 in the instruction execution, right? Now one of them will be picked and forwarded to the MAR as memory address. Now if we look at the control signals, select signal for the mux MA, that would be again set by the control circuit. If we are in step 4, it would be for the load store instruction, it means that we have the effective address in RZ that would be forwarded to MAR. Or if it is in step 1, then we are trying to access the memory using PC. So accordingly, the select line would be picked. Now the memory would respond us with data, which would be typically in MDR. That value will be sent to IR in the very first step, and the value in IR would be used by the control circuitry to generate all the other signals. And in step 2, in the same step, we are going to generate the immediate value and keep it ready. So the immediate value will be given to mux B, mux INC. Mux B for the data path and mux INC in the instruction fetch path, which will help us to generate the next PC, right? And if we look at the way MDR is picked in step 4, it would be the value in MDR would be driven as input to RY, typically for load instructions, and in step 1 it would be written to IR. So this is the fetch stage. Now let's look at the second step a little more in detail, which is instruction decode. Basically what the hardware would do is it would follow the instruction encoding given by the ISA. All it has, if you remember, is a 32-bit value. It would extract all the individual fields, for example, the opcode, function 3, function 7, immediate value, RS1, RS2, RD, etc. You can imagine that it might be using some bit masks. So if you are not aware what bit mask is, let's say you want to extract the 3 LSB bits of some particular register. What would you do is we would AND it with 0x7, right? So all the other bit positions would be 0 in the output. Only the LSB 3 bits would be extracted. So similarly, we can use different masks for different bit positions. And in the same step, after we use the bit mask, we have the individual fields. We are going to look at the opcode, function 3, function 6, function 7 as needed, and we would identify the operation that we need to perform, and we would also decide, we in the sense the control circuit would also decide what signal it needs to send to the ALU, basically which operation it has to perform, whether it is an add, subtract, left shift, right shift, multiply, divide, etc. And it would also send the signals to other muxes, right? Mux B, mux Y, mux INC, mux MA, etc. And in each step, what signals should be sent to each of these, right? All these would be decided by the control circuit, and it will also identify the register operands, source and destination, contact the register file, and keep the values ready in A and B. And it would also keep the destination register address as C ready to be used, right? And the immediate field, if you look at some of the instruction encoding, is not straightforward. For I-type instruction, the MSB 12 bits would give us the value, right? But not so for JL and sorry, JLR and SB and S type also. So we need to regenerate the immediate field, and we also need to sign extend it from 12 bits to 32 bits or 64 bits based on the ISA. And for branch and jump instructions, if you remember, we were omitting immediate 0 bit position. So we need to regenerate that basically by shifting it left by 2, sorry, by 1 position or multiplying it by 2. So all this work needs to be done by the control circuitry in the instruction decode step. Only then we will get all the other control signals for the remaining steps. Now, looking at the last module that would help us to execute instructions is the processor memory interface, PMI. Basically, it would need some control signals as generated by the control circuitry. Based on these control signals, it would transfer data between the processor and the memory. Right? It would need the address where it needs to go and get the data or write the data to. And if it is let's say an instruction fetch, then we would know that we need to fetch uh, 32 bits of instruction, 32-bit value, right? But if it is, let's say, load, then we need to figure out whether it is load byte or load half word, load double word, etc. So the granularity of access should also be specified to the processor memory interface for the loads and stores. Now, we expect all these operations to be completed in one cycle. It means that the processor would send the address to MAR. MAR will be sent to the memory. The memory would respond us with data, and the data will be placed in MDR, and MDR is sent to MUXY. Everything, all these operations. If the access to MAR and MDR can be neglected for the time being because they are registers and they are quite fast, but the response from memory is rarely this fast. It is very, very slow. That's what we are going to look at in module 3, that uh, the typical RAM, we call the DRAM, right? It would take thousands of cycles to get to get the data back to the processor. Now, in order to avoid this and waiting for the memory to respond, we introduce what's called as cache memory. And typically, cache is very fast. It is bigger in size than the registers, right? And it responds in one cycle if it is hit, and if the data that we are looking for is not in the cache, then we eventually need to go to the memory. At this point, just understand that we have a small storage unit between the registers and memory that is helping us to get the data in one cycle. Now, how it works and why it should work in the first place, all these I'm going to explain in module 3. Okay. Now, a quick high level view of the PMI. PMI has MAR, MDR. MAR would be sent to the memory. Memory would respond. That data will be placed in MDR. And typically, MAR can be imagined to have uh, the input from MUX MA, and the inputs to the MUX MA would be either RZ or the IAG itself, right? And MDR, when it replies, imagine that is a DMUX, which would be driving either instruction register or MUXY. And just like before, the control signal of, sorry, the select signal of these MUX and DMUX would be generated by the control circuitry. So overall, this is the data path that we have seen so far, how the data flow is happening from the registers to the ALU and to the memory and uh, back to the register file, right? All the black lines here are the data path, and the blue lines, which were earlier red lines in all the previous slides, are the control signals, the control path. And if we look at the processor memory interface, all the data flow is shown in the black lines, and all the control signals again are shown in blue. And this is the IAG. Typically, uh, the sorry, excuse me, all the data paths again are shown in black and the control signals are shown in blue. So together, these three small modules will help us to execute an instruction on the hardware, right? Basically, all these make up the hardware, and together they are called as the control path and the data path. These are the two basic components of the computer, right? Now, the overall data path that I've shown in the previous slide was from Carl Hamasher's textbook. That's what I have followed for this three lectures. The reason being, uh, in the computer organization and design risk v edition book that we were following earlier, uh, directly the figure on the slide is given. So it's a little complicated to understand if I present this right from the word go. But now you can make some inferences from uh, this flow. Basically, here we have the PC that would be given to the memory, and the memory would be giving us the instruction, which is 32-bit, and different fields from this instruction are given to the register file. uh, Basically, rs1 here, rs2 here, this is rd, and then the register file would give us the values a and b. Earlier here it is read data 1 and read data 2, and we had mux b earlier, here it is labeled as mux 1, right? Again, the controls circuitry would generate the select line. Both of these would be the input to the ALU, and the ALU's result, based on whether it is load or store, would be given to the memory or forwarded to the next step, right? Here we have the mux y, here it is labeled as mux 0. Again, the select line is given by the control circuitry, etc. And the adder you see here is uh, either it does it picks the offset either given um, from the branch, sorry, here is that slightly different, but the operation is same. It would pick PC or the offset given from the instruction, etc. Slight change, but the operation is still same. I'm going to skip this kind of representation for now, but I wanted to touch upon this because if you read the Patterson and Hennessy textbook, this is what it would present, right? Do not get confused, both represent the same. Now, if we are wondering how do we go about generating the control signals, there are two primary approaches. One is hardwired control, and another is microprogrammed control, which is more towards the CISC style ISA, or basically the hardware for CISC style ISA. I'm going to skip it for now, but let's touch upon the hardwired control a little. Basically, all the instructions have can be imagined as sequence of steps. That's what we have done, and in each step the instruction execution will undergo some specific things, right? For example, in the decode step, we are going to decode the instruction. In the execute step, we are going to execute the instruction, or using the ALU. In the memory access stage, we are going to talk to the memory, or if it is in ALU, we are going to just forward it to the next step, etc. So to keep track of these 5 steps or the sequence of steps, we can maintain a step counter. Now, the control signals that we are generating in each step would be depending on the output of the step counter. Basically, you can imagine that the step counter output would be 0, 1, 2, 3, 4. Again, back to 0, 1, 2, 3, 4. So when the step counter outputs 0, then the hardware would be behaving as if it's trying to contact the memory and get the value, write it into IR, and increment the PC, right? And if it is the step counter's output is 1, then the value in IR would be looked at, and it would be all the individual fields will be extracted to figure out which instruction it is and what all registers are being used, etc., and even the immediate field, so on and so forth, right? And at the end of step 3, we would have the result of computation and what to do, like with that, etc. Also, the hardware needs to handle some external inputs like interrupts. Now, at this moment, I'll just give a very high level example of what interrupt might look like. Let's say there is a power failure, or you press your powered button long enough that it shuts down. So how do we handle that, right? Or there might be some additional corner cases like a memory segmentation fault, etc. Now, how do we handle those kind of interrupts? So all this logic needs to be taken care of at the hardware. So the section 4.4 of Patterson and Hennessy textbook gives a very simple implementation example of hardware control. I strongly suggest all of you to go through it. It will definitely help you in the first phase of your course project. Uh, if you look at the Carl Hamischer textbook, the control circuit would look something like this, right? We assume that all the instructions are completed in 5 steps, so the step counter will be generating the signals T1, T2, T3, T4, T5 to the control signal generator, and to the control signal generator, basically it's a combinational circuit. The other inputs are the instruction decoder, basically all the masks to extract individual fields, and based on that determining what kind of operation needs to be performed, etc., would be done by the instruction decoder, and it generates the appropriate signals ins1, ins2, so on and so forth. For example, if let's say it's an add instruction, maybe ins1 would be set to 1. Let's say if it is a subtract, maybe ins2 will be set to 1. Accordingly, the control signal generator would generate all the required control signals that we saw earlier for the muxes and the MAR, MDR, etc. Right? So this is an example of implementation, just like what was given in Hennessy Patterson. This was given in Carl Hamischer. So here is the reading assignment for you all. I did not give you any reading material for the past 4 lectures, to be precise. So go through the chapter 7 of computer organization and computer organization book by Carl Hamischer, the 5th edition, and go through sections 4.3 and 4.4 of our regular textbook by Patterson and Hennessy. With that, I will pause this lecture. Thank you.